I think this is the last week, so and it will be quick because you already you have you've you already seen how to do a linear regression, how to fit a linear regression. So logistic regression is not that different. Okay, so I will just tell you what is the basic idea of doing logistic regression, and then we will just dive into our software. So okay, let's get started with logistic regression. So I think before we start, I just want to say that a lot of slides were taken from this book and this book and the lecture called Introduction to Statistical Learning with Application in R. So I guess we will have a little bit more formula, but we're trying to simplify now. Okay, so this is a good book, you know, to get started with the statistical learning and using R. Okay, so it's not talking too much about it is not about R, so but it has some introduction, a very short clear introduction to R, which is a basic R, which is quite different from what we are learning in this course, because in this course what we are learning is with the package-oriented approach, okay, which basically means mStat. So this is basic R. So basically, you will learn how how R works without using any software, without using any packages. So this is a very nice book. If you want to learn more about the linear regression, logistic regression, and also this is an introductory book to machine learning. Okay, if you prefer it, data science, whatever you call it. So okay, so I guess if you can fit a line, then you can fit a squiggle. Okay, so the idea is this is a scatter plot. Okay, this is also a scatter plot. Okay, the idea is when our outcome variable or explanatory variable is a numerical variable, and then when our when our explanatory as well as a response variable are continuous variable, we can make a scatter plot and fit them with a linear regression line, okay, using a least square line. So this is a review for a linear regression. Okay, the idea is we want to see how the two variables x and y relate to each other, okay, using one line. But when we consider about the response variable as a categorical variable, so you see the data are really, touching each other. So it's like a separate category from each level. So this is y, a6, this is a6, okay? So when we try to fit the linear regression, when we try to fit the linear regression, when our outcome variable is such a categorical variable, our linear regression line goes somewhat like this. Okay, so exactly our data does not fit it. Okay, because we have a categorical problem. Okay, so when we look at the linear problem, it is a prediction problem with the numerical outcome, okay, continuous outcome. And so this is called a prediction problem. This is called a linear problem, okay? But when we look at this, we have a categorical level, okay? The example here is it has two categorical levels, so we say it is a binary variable. But category can have many levels, okay? So if it is more than two, we can say this is a multinomial. We can say something like multinomial model, okay? It has many categories. So the idea is we want to fit a regression line, okay? But when we think about it, we can only have the we cannot have the mean, okay? What we can have is a proportion, okay? What we can have is a proportion, okay? So, but in our data set, we arbitrarily define 1 or 0, okay, 1 or 2 to indicate our category. So we can still fit our these variables using linear regression, but our linear regression line will look like the blue line, okay? But the idea is we want to fit all the values, okay? So we will transform this linear line, okay, to match the dotted black dark line, okay, to fit all the data. So this transformation is called the logic transformation, okay? So let's go back to the descriptive. When our outcome variable, when our variable is a continuous variable, we use mean, okay? We use mean. So the linear function is basically, it is a conditional mean, okay? It is a conditional mean. We look at the condition, when x equal to some value, and then we predict the mean of y, okay? So for each point, we predict like that. So for each point of x, we predict the mean of y, okay? What will be the best mean for y when x is equal to some value. So that is the idea. But here, we do not have a linear problem. We have a classification problem, right? We have to classify into 1 or 2 groups, okay? Either 1 or 2 groups. Oh, so we cannot exactly fit the linear, okay? So when our variable is categorical, what do we use as a descriptive measure? We have to use proportion, right? Frequency and percentages, which is the same as proportion. Okay, so proportion has a problem because it goes from 0 to 1. Okay, it goes from 0 to 1, which is limitation. Okay, so let's continue. Okay, so this is just a review of the linear regression. So we have weight and size, which are continuous variable, and then we fit a line. Okay, and then with the line we can ask a lot of things. Okay, we can answer a lot of things. Okay, first we can calculate R square, which is basically the square of correlation coefficient, and see if they are related. Okay, large value will imply the large effects. Okay, then we calculate p-value, whether this R square value is significant, and then we can actually predict first get a coefficient, intercept and slope, okay, to indicate this line, and then we can use that line to predict size, which is our response variable given weight, okay, which is our explanatory variable. Okay, so this is basically prediction, okay. When weight is equal to some value, and then we find the best mean value for size, okay. So this is basically what linear regression did. Okay, so now linear regression assume that our response variable is a quantitative, okay, continuous one. But in biology or in social science, very often we have response variable as a categorical variable. Okay, so we say this is a classification problem, not a linear problem. Okay. Okay, so far, so there are 3 most widely used classification model, but we won't cover them. We will cover the logistic regression, but you need to understand that there is a linear discriminant analysis, okay, which is called the LDA, which has some advantages over the logistic regression, but we won't discuss here, okay. Okay, what is the difference between logistic regression and this linear discriminant analysis? Okay, so linear discriminant analysis is basically the linear regression, and we code that we code our response variable. Okay, response variable is a categorical variable as with a numerical symbol. Okay, 1 2 0 1 something, and then we assume that it is the number, and then we fit in a linear regression line, and then we just say that okay, if it is we just calculated the probability of this linear regression line and assign into the category. Okay, that's why we discriminate the classes between them based on the probability. Okay, but for logistic regression, we still use the linearity, but actually what we did is we used the logarithm of odds. Okay, to make the linear to make the linear model. So basically, this is logistic regression is the linear model. Okay, linear model of logarithm of odds. But we will talk about that soon. Okay, quadratic discriminant analysis. Okay, so in linear relationship, assume the relationship to be linear. But when we do the scatter plot, when the relationship is non-linear, something like curve pattern, something like this. Okay, so we have this one and this kind of relationship. So this is exactly not linear. So in that case, we do we add a quadratic term to the linear discriminant analysis, and which is called a quadratic discriminant analysis. Okay, anyway, it is for knowledge, and we will discuss here. So we will talk about the logistic regression. Okay, so what is the logistic regression problem? Okay, so say we want to predict the medical condition of a patient, okay, on a basis of a symptom. So we look at her symptoms, we ask symptoms, and then based on the symptoms, we will predict their medical condition, okay, what kind of medical condition she present. So basically, what the researchers are interested in are three possible diagnoses, okay, stroke or drug overdose or epileptic seizures. So based on the symptoms, the response variable, the outcome variable will be the diagnosis, which is diagnosis will be three levels, okay, three categorical levels, which is stroke, drug overdose, and epileptic seizure. So of course, we can code them as 1, 2, 3 or 0, 1, 2 or whatever numbers we can give, okay? Because these are just arbitrary numbers. These are not real value, okay? And we will discuss that, why these are arbitrary numbers. So why not we use linear regression, okay? This is a, basically, if we look at the, R, the data where we, in numerical variable, but they are not numerical, okay? Because this code in 1, 2, 3, basically, if you look at that, there is an order, okay? Actually, if you really think about it, there shouldn't be any order, okay? So you can put 2 first and then 1 to the last, or whatever order you, there should be any orders. And then if you subtract 2 with 1 and 3 with 2, the distance should not be the same, okay? If it is a numerical sense, this always result in 1, right? 2 minus 1 is equal to 2, and 3 minus 2 is equal to 2. But the idea here is stroke is not 1 unit away from drug overdose, and stroke is not 2 units away from the epileptic seizure, right? Because these are the symbolic numbers, okay? We just give them as an arbitrary number. So there is no real numerical interpretation or calculation based on that. So that's why it's not a good idea to do a linear regression, because linear regression consider this variable as a real numerical variable, okay, and take the difference between stroke and drug overdose as one unit, okay, and the difference between drug overdose and epileptic seizure as one unit. So which is not the case in reality. Okay, so there is no particular reason this should be the case. We can give any coding we want, okay? And if we give, okay, if we use 1, 2, 3 and fit a linear model, it will give you one result, okay? And then if we give something like, okay, 50, 100, 150, and then it will give you a very different linear model based on the numbers, okay? So we really shouldn't use linear regression, okay? So there will be a totally different relationship if we give different numbers. And okay, that is the example with the 3 categorical level, okay? What if we have 2 categorical level, okay? That would be a little bit simpler, okay? Based on the symptoms, we have to classify either it is a stroke or it is a drug overdose, okay? So we have 2 categorical variables. So that's why we have consider this problem as a classification problem, okay? So we have to use classification methods. We have to classify either as a stroke or as a drug overdose. So actually there is a little bit of the mathematics, but let's try to look at this, okay? So how do we model the relationship, okay? So we model the relationship using the probability, which is the same as proportion, right? So we use proportion or frequency or percentage to describe the variable, and then which is the same sense as the probability, okay? So logistic regression is, again, it is just a conditional probability, if you remember from our week 2. Okay, so basically this is the probability of X, and then what is this? This is the probability of Y is equal to some value given X, okay? So if we have X value, what is the probability of Y equal to the outcome, okay? In our case here, we have the drug overdose, okay? So which is 1, we gave it 1, okay? So our logistic regression is basically a probability of getting our outcome as a drug overdose given X value is something, okay? And then we will recall the linear regression model, and we will build our logistic regression based on that linear regression, okay? So our linear regression, so I think here we have a little bit different annotation, right? So if you remember, we have Y, I think we have B0, right? If you remember, B0 plus B1 X, okay? So these are all the same, okay? So this is the same. So basically, the linear model state that we have the intercept and slope, and then X, okay? So we have this, and then we want to get this probability based on that one, okay? And that is a given. That is a given thought. Okay, so how does it work? Okay, so let's think about it. Let's basically our Y, this is Y. Okay, our Y only has 0 and 1. Okay, so obviously we cannot fit as a linear regression. Okay, so how do we do this? We transform this. This linear regression and link to the logistic regression using logit link. Okay, so how do we do that? So the logistic regression function, when the mathematician they try to figure out a way to calculate this, they come up with a formula. Okay, This is for the linear regression model, and this is the logistic regression model. So basically, logistic regression model is a probability model, probabilistic model. Okay, it is exactly equal to the exponential. This is the exponentiation. Okay, exponentiation of the linear term. Okay, so this is the linear term. So the logistic function is equal to the exponentiation of linear model. Okay, so this is one concept. Okay, so what is the probability? So if you remember, I think we have a slide later. So probability is the so basically probability is the number. Sorry, where is my notes? Probability is the this is the number. Probability or proportion is the number of event, right? Divided by sample size. Okay, so this can be considered as a sample size, and this can be considered as our event. Okay, so probability of our logistic function is equal to the exponentiation of the linear model divided by the 1 plus exponentiation of linear model. Okay, so how do we calculate this? We calculate this beta 0 and beta 1 by using maximum likelihood estimation. Okay, so if you don't understand that, I mean, there are a lot of I skipped a lot of detailed explanation. So just remember this. Okay, for every model we have intercept and slope. So for the linear model we have beta 0 and beta 1, and this is the linear term. Okay, for the logistic term we have exponentiation of the linear term. And how do we find this? How do we find this intercept and slope? In logistic function, we use maximum likelihood estimation methods. Okay, for the linear regression, what do we use? We use least square regression method. Do you remember? So least square method. Okay, least square error method. Okay, so again, this least square error method is also a special case of maximum likelihood method. Okay, so they are just a different, I mean, they are just an upgraded version of the linear least square line method. Okay, anyway, so so what is a logistic regression? Logistic regression is using logistic regression use linear regression with the logic link, okay, with the logistic transformation, so that it can use the linear function of the linear model. Okay, basically our dependent or explanatory variable is a logistic transformation, and basically if it is a binary variable, we have 0 and 1 assigned. Okay, if 1 is our outcome of interest and 0 is the complementary, I mean, event, right? So think about this. Okay, if we have 1 and 0, and when we find the mean is equal to the proportion of this this outcome. Okay, this is just a mathematical sense. Okay, so what is the proportion? I already talked about it. Proportion is P, which is equal to the number of event divided by sample size. And then actually P has a limitation, because P only goes from 0 to 1. Okay, P only goes from 0 to 1. So that's why we need to calculate odds. Okay, odd is basically P divided by 1 minus P. Okay, so that's why we see here probability is this one is the odds. Okay, basically the odds in the logistic regression, odds divided by 1 plus odds. Okay, but okay, let's leave it there. Okay, so consider if we have 10 values, okay, 10 points, and then we have 1 values, okay, and 6 0. So our proportion is 4/10, which is easy, okay, 0.4. And then our odds is basically p divided by 1 minus p, okay, which is 0.6 divided by 0.4. 0.4 divided by 0.6, which is around 0.666. Okay, so basically what we did in logistic regression is we calculate this and then we give it a logarithmic of odds. Okay, so why odds? If we use odds, we can use the linearity terms. Okay, so let's continue looking at it. So basically our linear function, okay, L is equal to the logic link, okay, of the probability. Okay, so we connect the linear function using the logic link and connect it to the probability. Okay, so after all, we got this log of probability divided by 1 minus probability. Okay, so why that is the case? Okay, if we look at this, our probability only goes from 0 to 1. Okay, 0 to 1. But okay, if we change the log, if we use the logic link, it goes from minus infinity to plus infinity. Okay, which is basically a numerical number. Okay, which is basically a numerical number. So our variable, dependent variable, will become the numerical variable, continuous numerical variable, which range from minus infinity to plus infinity. So that's why we can fit a linear model using the logic. Okay, and after that, we have to convert them back to the probability by exponentiating. Okay, so this is the logistic transformation, which is the inverse of the logic transformation. So basically, we are playing, right? So we first change the probability to probability to get the linearity of the number using logic transformation, and then we will transform back to the p using the logistic transformation. It's just a name. Okay, so we can do like this. So what is the probability? It's a logistic of this log model, logistic model, and then which is basically equal to the exponentiation of the logistic of the L, and then which is exactly equal to the exponentiation of L divided by 1 plus exponentiation of L. Okay, so we already seen this. This L is equal to the linear model, right? Beta 0 plus beta 1 x. Okay. Okay, then after some manipulation, we got this. Okay, so we now know that odds is equal to this linearity. Okay, and then this quantity is okay. So this is, we already explained this. So this is what I explained earlier. So this is the logarithmic form of odds, which is equal to the linearity terms. Okay, so logistic regression is basically a continuation of the linear regression, but we just transform the limitation of having only two levels of categorical variable, and then we try to use the linear regression by transforming it using logic link. Okay, so that is the basic idea here. So how do we interpret this? Okay, so the way we interpret this, and the way we interpret in linear regression is, so beta 1, which is a slope, we give us the average change in y associated with 1 unit increase in x. Okay, but in logistic regression, basically 1 unit increase in x give us the increase in log odds. Okay, log odds. But basically, it is a little bit difficult to understand log odds. So that's why we transpound it back to the odd ratios, basically. So basically, after all, logistic regression is shown by an odd ratio. Okay, but when you look at this, the original outcomes without the transforming to the odd ratio by exponentiation, then these are interpreted as a coefficient. Okay, these coefficients are in terms of logarithmic or odds. Okay, so basically that is the idea. So our explanatory variable has two levels. Okay, 1 and 0, and then as always with a categorical variable, when we interpret it, we have to set one level as a reference. Oh, that's why it is a comparison. Okay, when there is a comparison, we divided these odds. Okay, so essentially it is transformed as the odd ratio. But anyway, this is how the logistic regression mechanism works. Okay. So after all, beta 0 and beta 1 are unknown. So we have to use the sample and estimate that. And how do we estimate this intercept and slope? We use the maximum likelihood. So what is the maximum likelihood? So basically, it maximizes the likelihood function of getting intercept and slope. So basically, maximum likelihood is looking at the data, and given this data, what is the probability of getting the best intercept and slope? Okay, so these methods try to get the best intercept and slope. So this is basically called a maximum likelihood function. Okay, so least square for linear regression is a special case of maximum likelihood estimation. So actually it follows the linearity, but the variable itself does not follow. The logarithmic forms follows the linear function. Okay, so the assumption for the logistic regression does not have to follow the assumption for linear regression. Okay, so like the linearity of the residual, normality of the residual, and the constant variability of the residual does not apply here, do not apply here. Okay, but it has its own assumption. The first one is the response variable must follow a binomial distribution, which basically is our outcome variable has to, follow binomial distribution mean basically it should has two outcome or two level. Okay, 1 or 0, or in our case is stroke or epileptic something. And then logistic regression assume a linear relationship between independent variable and the link function. Okay, so that's why we do not have to follow the linear assumption of the linear regression model. Okay, because it is indirectly indirectly assessing the relationship, linear relationship between independent variable and the logic. Okay, so actually we do not have to test this kind of assumption, but we can look at the scatter plot of the individual variable and the logic output. Okay, which we won't do here. Usually we don't assess the assumption. Okay, and the dependent variable should have mutually exclusive or exhaustive category, which basically means each level should be mutually exclusive. Okay, so it's like it is either pure or it is not pure. Okay, it cannot be both pure and not pure, and it is either stroke or it is either epileptic something. Okay, so it should be mutually exclusive and exhaustive. Okay, so in the next session, we will be looking at how we will be using this data set. Okay, which is basically a study. Okay, so a researcher is interested in GRE, which is a graduate record exam, and GPA, which is a grade point average, and the prestige of the undergrad institution, and how it affects the admission into the graduate school. Okay, so we will use this data set and look at how we can run logistic regression. So this will be a very quick session. So I don't think we need many days to finish this. Okay, so I think the theory is the basic idea behind the logistic regression is this one. So it basically used the logit function, logit link, to try to transform the dependent variable so that we can make use of the linear function to calculate our intercept and slope. Okay, so basically it's a continuation of the linear function, and then we have to transform back to this whatever logit link back to the our probability for the logistic function. Okay, so that is the basic concept of the logistic regression. And then the model selection, the hypothesis testing, confidence in our everything is the same. The same mean concepts are the same. But if you want to look at the details calculation, the formula, then I think you have to read details in the textbook, okay, or even Google it. But I think the concept is important here, not the calculation methods, but you need to understand how we get the intercept and slope. So we get the intercept and slope by using maximum likelihood estimation. Okay, which is a more stable statistical properties. And this more than the linear, least square regression. Okay, for linear regression model, we use the least square regression line method. Okay, we use the minimum error, square error, or residual, square error between the predicted and the observed value. Okay, so I think the first session is already time's up. So in the next session, we will, okay, so first, let us go to our local drive C, and then we will open our folder SCI_SWR. Okay, and then let's copy one. I think let's copy this one. Okay. Just copy one. Okay. It doesn't matter which one. And paste it, and then rename it as W4. So this is week 4 and day 1. Okay. Okay. So double click and open the file. Okay. And then what we will do is we will just delete it. We will just remove everything. Okay. And then we will start clearing our workspace. So whenever you create a new file, you should start with this line. Then we will load the library, load the packages. Okay, and then library mStats, that is as usual, and then library migrate up. Okay. Okay, so let's run these, and then we will load a different data set. Okay, we will import a different data set called the admission data. Admission data set. Okay, so I will share you the link. Okay, so I will share you this one and do a checkbox. Okay, so let's run this again. So we should see we have admission data set, okay, with 400 observation and 4 variables. So this is the data set that I described in the last slide. Okay, so as soon as we import our data set, we should check the scope, okay, or check data set. So codebook and admission. Okay. Anyway, we have admit. Okay, admit, which is our response variable. Okay, whether it is admit or not. So let's just summarize it. Okay, summary measures. Okay, so all 4 variables are numeric. So we will just do a sum. Okay, which is a quick sum. So we just give this admission. Okay. So we got admission, okay? We got admission variable. So no missing value. And admit variable start from 0. Okay, you see minimum 0, maximum 1. Okay, which is basically what we have set in our slide. Okay, so we have coded 0 and 1. Okay, 1 is admitted to a graduate school. 0 is not admitted to a graduate school. Okay, 0.3 is the percentage. Okay, percentage are admitted to the graduate school. Okay, so this should be the same as tabulation. Okay, so we will tabulate admit, tab admission, and then we say admit. Okay, because we need to specifically mention this variable because it is a numerical variable. Okay, R code R look as a numeric. So if you just leave it with the data set, then it won't appear. Okay, we have to specifically call this to tabulate it. Okay, so you see we have around 30% of admission. Okay, which is correspond to the 0.3. Okay, which is 30%. So if we coded the variable, binary variable as 0 and 1, then we can use mean is equal to the proportion of the response category. Okay, so this is what we mean by this slide. Okay, so we now get our response variable. So we say this is the response variable. This is response variable. And we need to check a little bit about other variable too. Okay, so GRE we have mean 587, but so median mean and median are not that far away from each other. And then we have a minimum and maximum value to 220 to 800. Okay, GPA around, okay, median around 3.5, and then minimum value 2.3 and maximum 4. Okay, GPA 4. So GPA should be 4. And then we got a rank, which is coming from the minimum is 1 and maximum is 4. Okay, so rank here is the rank of the undergrad school. We probably high school. Okay, prestige rank of the school of these students. Okay, so and we need to look at that too. Okay, so we will say rank because rank is a categorical variable. Okay, so I don't remember which one is high or not. Okay, anyway, we will see. Okay, we will see rank 1 is the highest one. Okay, rank 1 is the highest one, and then 2, 3, 4. Okay. Okay, so now we have looked at our data set. Okay, and then we will do some modeling. So first, I will demonstrate. Why don't why not fit into linear regression, right? So actually you can fit it and it will give out a result, okay? Because these are all numerical variable, okay? These are all numerical variable, and R will give you a result, but you cannot use I mean, it's quite tricky to interpret the result, okay? So you can still use that. So regress, and then our data set is admission, and then we got our response variable is admit, and then we will say, okay, which one first? We will say GRE, okay? So when you run that, you will have this kind of output, right? So actually you can interpret it the way we interpret as usual, okay? But it is still wrong, right? Because we cannot fit it because the admission is only 2 category. So the way we interpret linear regression is 1 unit increase in admit, okay? Oh, sorry, 1 unit increase in GRE where increase 0.001 increase in admit, okay? Which does not make any sense, okay? Because we only have two levels, okay? So it doesn't make sense at all, okay? But you can still run it and see the result, okay? So not good. So we need to fit into the logistic regression. Okay, so how do we fit into the logistic regression? So we will use another function called the logistics, okay? Logistics, like the logistic company. Okay, anyway, logistic, it produced the regression outputs and mirrors the SATA. Okay, basically it is a logistic output, and basically it's the it is a regression model, and by default it will give you an odd ratio. Okay, so the output of the logistic regression is the odd ratio, and then you can also calculate the coefficient, okay, which is the logarithm, I mean the log odds. So first we will calculate the log odds, okay? Calculate coefficients. So we just in log odds, okay? You need to, you can calculate anything you want, but as long as you know what you are doing, okay? So let's first do this, okay? Logistics, and then the same, you specify your data set, so admission, and then the response variable is admit, and then we will start with GRE, okay? One variable at a time. And then we mention odds should be odd ratio equal true. Oh, sorry, false. Okay, we want to get the, okay, we want to get the coefficient. Okay, and then we run this one. Okay, so which is pretty close, right? Pretty close to the linear output. Okay, remember it's 0.01, but this is in log odds. Okay, not the probability. Not the, yeah, probability. So how do we interpret this? Okay, how do we interpret this? So we have admission as 0 and 1. Okay, 1 is admitted to graduate school. Okay, so which is our outcome of interest? Okay, which is our outcome of interest? So which basically means that 1 unit increase in GRE give us 1 unit log odds increase in sorry, this 0.004 increase log odds, okay, of admission to the graduate school. Okay, so basically this is given 1 unit increase in GRE, we expect 0.004 increase in log odds. Basically have no, I mean, I'm not that, I do not have the kind of understanding about log odds, so I really don't understand what it means, right? So That's why we need to transform to odd ratio, which gives us a pretty nice idea of, I mean, we can comprehend odd ratio rather than log odds. Okay. Okay, so why don't we copy this, and then we will say, okay, this is, we calculate odd ratio. So this is calculating odd ratio by fitting logistic regression. Okay, and we will do this to true. Okay, or you can just delete it. And then when you run it, this will convert to odd ratio. Okay. So basically what it means that, okay, now we have now odds. Okay. How do we interpret the odd ratio? Okay. So odd ratio is always compared to 1. Okay. In short, it is odd ratio. Okay. What is our odd ratio reference? Is always 1. Is always 1. Okay. Which is basically there is no difference. Okay. But if you remember, when we fit in the linear regression, our null hypothesis is our null value is 0, right? We check whether this value is equal to 0 or not. Okay. But when we are talking about the odd ratio, which is a ratio, so a ratio should always be equal to 1. Okay. So odd ratio 1 means that there is no relationship. Okay. So what we have to do is we have to subtract from 1 to the our corresponding odd ratio. Okay, and then 1 minus odd ratio, and then we convert them into percentage. Okay, and then we multiply with 100%. So this is basically how you interpret an odd ratio. So how do we interpret it? So given 1 unit increase in GRE, we expect 4%. Sorry, 0.4% increase in 0.4% increase in odds of admission to the graduate school. Okay, so we know that, okay, GRE also play an important role in admission. Okay, GRE play an important role in admission. So we have a p-value 0.0002, which is significant. Okay, so we say that, okay, this value is not equal to 1. Okay, and then when we check the confidence interval, 95% confidence interval, and the null value 1 is not within the 95% CI. Okay, so we know that our data support that it is not equal to 1. Okay, so we have a significant predictor in a univariate or bivariate analysis. Okay, so we call this unadjusted analysis. Okay, because sometimes the univariate or bivariate analysis is just confusing. So we just say it is unadjusted analysis because we didn't control other variables. Okay, unadjusted logistic regression. Okay, so this is how you interpret it. This is how you look at it. Okay, and then so why don't we do this? Okay, so why don't we select model variable by forward model selection method. Okay, so we add to the model one by one. Okay, so we got GIE. So next step is our, okay, I think this is just an example, so we will give you this. Okay, GIE, and then we will save this as log m DRE. Okay, and then what will we do? We will run another three times for GPA, right? Now what is the next one? Uh, okay, GPA and rank. Okay. So actually, we'll say this is GPA and this is G rank. Okay, and then what will we do? We will compare. Okay, we will compare model. Compare models. Okay, so using the STTAB. Okay, estimate deviation. So we will say log m dot GRE, log m dot GPA, and then log m dot rank. Okay, then okay, wait, we need to run everything. So GR, so we will say and adjust that logistic regression of GRE, GPA, and it's a good idea to comment to write something. Okay, so finally we got this one. Okay, so you see every variable is significant. Okay, every variable is significant. And when you compare the model, you can see the AIC value, okay, the lower the better, right? So we got, we can use the last one and then continue doing this, okay? But if you remember, is a, our rank is a categorical variable, okay? But right now, logistic regression tree is it as a continuous variable, numerical variable. So we need to change that, okay? We need to change that. So how do we change that? Let's go back to here, okay? When we read the data, we will convert rank to factor version, okay? So this time, actually we can convert it to, anyway, we can convert it to the character version, and see if it is working, okay? Character version or rank. So how do we change that? We say admission, okay, and then add it to piping, and then we use replace rank, and then character version, so it's as dot character, okay, and then rank, and then we need to assign it back to admission, okay. So we will say admission, then assign, okay. So actually we make changes I mean in an earlier session of our R script, so we need to run everything again, okay. So Control A, which to select all lines, and then run it again. Okay, so now it works, right? So compared to rank 1, okay, compared to rank 1, so this has become 0.472, okay. So how do we interpret this? So rank 2, we have 0.0472, which is an odd ratio, okay. So if we interpret it, we have to minus 1 minus, okay, 0.472, which give us around what, 826 and 628, right? Am I correct? 628. We can just run this. Or 528, sorry. Okay, and then we convert it to 100%. So we just around 52.8%. Okay, so our what is our interpretation? So compared to rank 1, okay, which is not here, rank 1. Okay, so compared to rank 1, okay, I think a little bit off. So given 1 unit, oh, sorry, not given 1 unit. Compared to rank 1, being rank 2, it is below 1, right? So if our ratio is greater than 1, you got more chance of getting into the getting into the graduate school. If it is lower than 1, then your chance is lower. Okay, so being ranked 2 lower the chance of, or the odds of, getting into grad school, to graduate school by 52.8%. Okay, so the same. Okay, so compared to rank 1, this rank 3 reduced the chance of getting into the graduate school by 1 minus this value. Okay, and then the same. Okay, so rank 1 is the highest one. So compared to the highest one, the rest of the rank were perform lower, right? Lower chance of getting into the graduate school, which makes sense. Okay, so based on this, I think we do not even need to do. Okay, actually, let's follow our step. Okay, so we found that all 3 variables are important. Okay, so we just have to add everything, because everything is important, everything is significant. Okay, and you see that the here if you remember, in linear regression we have the f-test. Okay, we're just looking at the variance, but in logistic regression we use the likelihood chi-square. Okay, so we look at the model and compare the likelihood ratio of this model and the empty model and calculate the chi-square and the probability. Okay, so all probability are important, meaning that these variables are important. Okay, and we got the pseudo r square, which is basically the same as r square, just the r square, and this perform very low. Okay, and here we can also compare the log length, but basically we use the ANC value. Okay, so basically we can if we look at this, okay, looking at the ANC value, we can say that we will use 482. Okay, 482, which is the ranked version. And then step 2, we add variable again to model weight rank. Okay, model weight rank. So what is our model weight rank? So this one. Okay, so we have this one, rank, and then we add the first one. What do we add? GRE. Okay, and then we will copy this, and then second we will add GPA. Okay, and then we will call this log m RG. Okay, RGE, and then we call this log m dot RGPA. Okay, it is a matter of naming convention, so you can give whatever you want. Okay, so anyway, and we will compare the model again. Okay, so we will compare the model, compare models, and then how do we compare models? As TTAB, and then we will say log m dot. So we have to use this one. Okay, first IN rank, and then log m dot GRE and GRE, and then log m dot RGPA. Okay, so when you run that, so you can see that we have a pretty nice matrix here. So, and you can compare the ENC value. Okay, so our model will rank, rank only have 482, and then when we add the either variable, it performs well. Okay, better than with the only rank variable as the only explanatory variable. So anyway, we will use the lowest one, so we will use this one. Okay, and then we copy this, and then we go into step 3. Okay, step 3, which is basically adding the GRE. Okay, so imagine this. Okay, imagine if you have 20 variable, so you have a lot of combination, So which is not a good idea to use this for this model selection method. Okay, just use the expert opinion, because we just want to look at the association. So that is the best method. Anyway, so this one is the final model. Hopefully, we give the final model and run this. Okay, and then we compare the two. Okay, compare models. How do we compare model? Sorry, EST, TAP, and then what is our last model with the GPA? Okay, so we will copy this and then say log m dot final. Okay, so let's see how our final model is doing. Okay, so the final model is doing pretty well, right? The lowest ANC value, and then every variable is also significant. Okay, so this is how you fit a logistic regression, and everything in it. And this is also simply, logistic regression with one explanatory variable and also multiple logistic regression. Okay, so this is called a multiple logistic regression, and or you can call it or adjusted logistic regression. Okay, because we adjust by adding other variable, so we control confounding variables. Confounding variables. Okay. So I think this is the end of the logistic regression. Only one day. So any questions? I think we have a little bit heavy on mathematics. Anyway, I think you will get the idea of logistic regression. But I think I mean this is not the end of the journey. Okay, this is just the start of the 1,000 journey of statistics. So I think at least you will have you have an idea of what certain things are in statistics, and so that when you learn yourself in the future, then you won't be you'll be confused, or at least okay, at least you will think yourself, okay, I know that terminology. Okay, at least. Okay, so no questions, I guess. Of course, I will share you this R script. So the idea and the idea is quite the same. Okay, the idea is quite the same to the linear regression methods. And tomorrow's, I think we will spend a little bit 1 or 2 more days, okay, before we end this course. And because this is how you run logistic regression using mStats, okay, but we haven't covered how to do that in base R, okay. And I also want to share a little bit of basic R, okay, not base R, basic R, so that you have a clear understanding of why we do certain things, okay, why we subset certain things in a way. So I think that will explain a bit in this rather short course. Okay, so actually this is the end of the statistics with R. So but I will spend one or two more days, okay, to look at how we can do this logistic regression in R tomorrow. And then I talk about what basic are, okay, and what kind of data types are there, and if we want to do certain things in R, what can we do, okay, using R? What is out there in R, in real R, okay, not mStats, okay. So if you want to join it, you're more than welcome to join. Okay. So the same hours, but I think this pretty much sums up the statistics with R. Okay. So no question, I guess. Do you have any questions? Or perhaps you can share what you think of the course. Okay. We can say this is the end of the, this is the last day of the statistics with R. So if you want to share your feeling of the course, or if you would like to give feedback of the course, you're welcome to do it.
It was very good, actually. I liked it.
Sashik, thank you. So any expectation that doesn't matter?
For me, no, because I have to, I read it once, but I have to revise it. So it's a basic thing that I learned. So it was a good experience for me.
Okay, I'm great. I'm glad to hear it. Actually, to other participants joining this course, if you don't know, Sashi and Sashi and I are attending the same school, honestly, same university in Thailand. So actually, we have this, the same art training in our class last year. But I think this one is a little bit different. What we have learned last year, right?
Yes.
So basically, it's a different package.
Yes.
Hello.
Yes.
Yeah, if I may, I think it was a very good learning course. I'm very, very grateful for all the inputs and the effort that you have put into it. And I think for someone who actually do not have any experience with research or some, the basics in this, I think in the beginning we had a lot of participants, but towards the end, I think there are only few. So I think most of them left one way or other, but I think they will follow up on YouTube and your records. But I think someone without this basic, I think my colleagues here in my station, I think they left because it was quite difficult for them to catch up. So, but for someone who have kind of a little bit experience and knowledge on research and some basics, I think this is a great course. So I just want to thank you. And definitely, if you have any problem, we will definitely get back to you. And we also look forward for similar courses if in the future. Thank you.
Okay, and thank you very much. I appreciate the feedback. I think that is that is what we usually see when something like statistics and art are combined into the course, right? And after all, these are not mandatory. Like you do not get any credits, or you do not get you don't even get a certificate at the end of the course. So I think so. You are pretty. You are quite right, because when we start this session, I think we have around 48 participants also, but right now we got 5.
Yes.
5 including me.
Yeah.
It doesn't matter. Okay, it doesn't matter. And anyway, I think this is a way to learn and share. And I don't see. These are all should be practical. And for someone who should, for someone who wants to get some knowledge in statistics, at some point they would just stop. If they are not really keen on learning statistics. Actually, this topic is a really, I would say, a cruel subject because statistics itself is a very hard topic to learn, right? And R is Pretty much like programming. So a lot of writing codes. I mean, it's like for most people, it's like an alien language. So when you combine these two together, so that's pretty cruel.
Dr. Miu?
Yes.
Yes, this is Pema actually. I
Yes,
couldn't
Velma.
speak actually in the beginning, but because I'm part of the health program, actually currently working in the MCH program, I would find this quite useful. And I'm also part of Bhutan, Be Smart course, and I have just got my data ready, and I'm so excited that at some point of time I may be able to use this to basically analyze the collected data. So I would like to again join my colleagues to express my gratitude for introducing me to this very important and useful software. But I'm sure like this is not going to be the end. I'll keep on joining you. Yeah, thank you.
Okay, thank you. Great to hear it. So actually, I mean, the one who initiated this call is Stanley Dodgy, I think. I think he's busy somewhat. Anyway, okay. I think time is almost up, so we will stop here now. So tomorrow, if you're welcome to join. So we have a session on using basic R. Okay. So actually, I appreciate all the efforts. So thank you for participating, and see you tomorrow. And